Hey, good morning, everyone. Today we'll discuss compressive strengths of concrete and what are the influencing factors to affect the strength of concrete. So many of these things we have discussed before. Today we summarize these factors and talk about them in more details. First of all, let's review the basic knowledge about behavior of materials under compression. Okay, so this is something we learned from CE370. Okay, so this is a concrete cylinder which is under compression load. Okay, the stress sigma is equal to the force divided by the areas of the cylinder, and the strain epsilon is equal to change of the length of the cylinder in the direction of the force over the original length of the cylinder. Okay. When the concrete is under compression, vertically, a dimension will become smaller, but horizontally, in the x direction, it will expand somehow. Okay. So the strain in the x direction, we call that epsilon x. Okay. The strain in the y direction is called epsilon y. And the sign of epsilon x and y are different because one is under compression, the other one is under tension. Okay. The absolute value of epsilon x or epsilon y, we call that Poisson's ratio. For concrete, the Poisson's ratio is around 0.2, from 0.18 to 0.2. Okay. When the concrete cylinder is under compression, initially the slope of the stress and strain curve is straight. Okay. But microcrack will begins at around 30% of the final load. Okay. And after microcrack begins, the slope of the curve becomes smaller until the final load, which is the load, make the concrete to fail. Okay. And after that, the resistance of concrete to stress becomes smaller, but it can still resist some of the load until final failure. The volumetric strain, which is defined as change of the volume of the specimen over the original volume of the concrete, is calculated by this. Okay. The volumetric strain epsilon V is equal to the strain in x, y, and z direction added together. Okay. Remember, the sign for the strain could be positive or negative. Okay. Under compression, we call it positive. Under tension, we call that negative. Okay. So you can use this equation to estimate the volumetric strain. Right. The influence factors of the strength of concrete, there are many of them. Okay, as we can see from here, including cement properties. Okay, the composition of clinker. Okay, the microstructure of clinker, the percentage of gypsum, PSD is particle size distribution, and of course water to cement ratio. Okay, so water to cement ratio is the most important factors of all of them controlling the strength of concrete. Okay, air content, admixtures, even the mixing conditions. Okay, how well you compare the concrete, curing conditions, what is the curing temperature, okay. What is the curing method, and even the manner of testing. All of these factors can more or less affect the strength of concrete. Okay, today we will go over many of them. Okay, let's look at the water to cement ratio first. Okay, so based on the famous Abraham's law, which is more than 100 years old, the strength of concrete is proportional to the volume of cement, volume of water, and volume of aggregate. Okay. Another version of the equation we can see from here. Here is the water to cement ratio. A and B are constant. Okay, for A is the empirical constant. The value is around 96, 97 megapascal. Okay, for B is also constant value. Is around 4, but we can see here water to cement ratio has very strong effect on the strength of concrete. Okay, we increase water to cement ratio, the strength of concrete will go down. On the other hand, when we reduce the water cement ratio, the strength will go up. Okay. However, keep in mind, when the water cement ratio is very low, it is very hard to fully compact the concrete. Okay. If the concrete cannot be fully compacted, even though the water cement ratio may be very low, the strength cannot be high. Okay, so keep that in mind. Okay, this figure shows us how the hydration age in hours of concrete with different water to cement ratio affect the strength of concrete. Okay, for all the concrete at all age, when we reduce the water cement ratio, the strength will increase. Okay, so water cement ratio of 0.5, the concrete has higher strength at all ages compared to concrete with lower water to cement ratios. Okay, and we can also kind of estimate the strength of concrete at a certain age based on ultimate strength of concrete, some constant, and the time of interest. Okay, T0 here is the age at the starting of the strength development of concrete. You can think this as the initial site time of concrete. And here shows again how the strength will increase over time. The strength can be estimated based on either compressive strength, okay, or we can use some non-destructive testing methods such as ultrasound to estimate the strength of concrete. Okay, so here are two curves. One curve is based on the strength of concrete, but when the strength of concrete is very low, using a compressive machine, we cannot tell the strength, okay, at very early age. But we can do that using non-destructive testing methods such as ultrasound. Okay, ultrasound method can monitor the strength at early age compared to the machine. Okay. Here is another curve for concrete with different water to cement ratio, hydration age, and also the stress. Okay. At the early age, this is up to 20 hours. We can see the slope of the curve are quite different. Concrete with lower water cement ratio, the slope is steeper, which means the increase in strength is faster for concrete with lower water to cement ratio compared to concrete with higher water to cement ratio. Okay, so but for all the concrete increased hydration age, the strength will be higher. Okay. Then let's look at cement composition. This is old knowledge. When we increase the C3S%, okay, we will have higher early age strength, but lower final strength. Higher C2S content, we have lower early age, but higher final age strength. Okay, we talked about this in early lectures. That is because the hydration speed of C3S is faster compared to C2S. Okay. Another thing is about particle size or the fineness of cement particles. Increase the fineness of particles by reduce the particle size. Okay, we will have a higher early age strength and also higher final strength. Okay, when we reduce the particle size, the surface area is higher, so we have more contact area between the water and the cement. So we have more hydration goes on. We have more hydration product. So early age strength will be higher. For the later final strength, because we reduce particle size, it is easier for the inner core of cement particles to be dissolved from water. Remember the three words: dissolve, diffuse, and precipitate. Actually, when the particle size is too large, larger than 60 micrometer, the inner core of cement cannot be dissolved by water because it is very hard for the water to penetrate deep inside and dissolve more ions into the water solution and get hydration goes up. So cement particles larger than 60 micrometer contribute very little to the strength of concrete. So increase the fineness, increase the surface area by reduce the particle size, we can increase both early age and also final strength. So that is cement composition. Then let's look at aggregate. Okay, so we know aggregate should be an inert material, which means it should not participate with hydration. Okay, but aggregate actually can affect the strength of concrete. Okay. When we reduce the maximum size of aggregate, we will reduce the stress concentration around the boundary of cement, cement paste and aggregate. So that will increase the strength of concrete. Okay. Reduced particle size will also, increase the strength of aggregate will also increase the strength of concrete. Now this is for high strength concrete only. For normal concrete, increased strength of aggregate, we could not increase strength of concrete. So why? That's the reason. Let me share the screen with my iPad. Okay. All right. Okay. So the reason is because in concrete, we have cement paste, right? What we call a paste. We have aggregate, and we have the boundary between the cement paste and aggregate, which is, we call that interfacial transition zone, or ITZ. Okay, we have three parts in concrete. The strength of concrete depends on the weakest of these three links: paste, aggregate, or ITZ. For normal concrete, the weakest link is in the ITZ, or the cement paste. As a result, when the concrete has a crack, it will generate at the weakest link, which is the ITZ, or the paste. And when the crack propagates, it will try to find the ITZ again. So this is the crack patterns we see for normal concrete. Okay. On the other hand, for high strength concrete, the weakest link may become the aggregate, because for high strength concrete, we use silica film, we use low water cement ratio to increase the strength of paste, okay, and also improve the strength of ITZ. And because of that, the aggregate becomes the weakest link. As a result, the quad will try to find the weakest link, which is the L gate in high stress concrete. So we call that weakest link theory. Okay, come back to the questions. For high strength concrete, when we improve the strength of L gate, we improve the weakest link. So the strength of high strength concrete will be higher. However, for normal concrete, the weakest link is the ITZ, or the boundary between the paste and L gate. If we improve the strength of L gate, we do not improve the strength of the weakest link. So the strength of normal concrete will not improve as much. Okay. Third part, the surface texture. The surface texture that will improve the ITZ. Again, ITZ is called interfacial transition zone, the boundary between the L gate and the cement paste. Okay, so rough surface texture will improve the strength, okay, especially for tensile stress compared to compressive stress. Okay. So L gate can also affect the strength of concrete. For mineral mixtures, I think we discussed this before. For flash slag, we will have lower initial strength, but higher final strength. This is because pozzolanic reaction. Okay, for pozzolanic reaction, it is slower, so initial strength will be lower, but the final strength will be higher because pozzolanic reaction transfer calcium hydroxide into CSH, so make the concrete stronger. For silica film, it will increase both early age and the final age strength. Okay. That is because for silica film, it is very reactive due to highly reactive silica and also due to the small particle size. Okay. So we have faster hydration rate. So that will offset the slower reaction of pozzolanic reaction. Okay. And silica film can also reduce the porosity, refine the pore size, okay, and also improve the particle packing because the particle size of silica film is much smaller. It can fill in the interparticle space between cement particles, okay, and also improve the ITZ zone. Again, this is not new knowledge. We discussed this when we discuss mineral mixtures. For chemical mixtures, okay, we also discussed this before. When we use water-reducing agent, if the function of water-reducing agent is to reduce the water requirement, so we have lower water-to-cement ratio. So the strength will, of course, increase because, again, water-cement ratio is the most important factor affecting the strength of concrete. But even if we do not increase the water-cement ratio, because superplasticizer can improve the dispersion of cement particles, get rid of the entrapped air, so we may also improve the strength of concrete. For accelerator and retarders, they have no significant effect, but they may have some minor effect because remember, temperature has effect on strength. Increase the temperature will increase early age strength and reduce the final strength. When we use accelerator, it has the same effect as higher temperature. So it will increase hydration speed. So by using accelerators, we increase early age strength, but reduce the final age strength. For air entraining agent, because it will increase the porosity by introduce the entrained air, so the strength will decrease. Okay, so here shows how the curing temperature affect the strength of concrete. This is concrete cured at different temperature, 15, 25, and 30 degree Celsius. Okay, so increased temperature, the early strength will increase, but the trend will goes down. Okay, concrete cured at lower temperature will catch up with the stress. So here, how the humidity affect the strength. Again, this is old slides. When we increase the time for the concrete to moisture cured, the strength will keep goes up. Okay. As long as we air dry the concrete, the strength development will stop quickly, as we can see from these curves. All right, so this is something new, testing parameters. Okay, so when we check the strength of concrete cylinder, we put the cylinder in a compressive strength machine. Okay, the machine compress the cylinder from top and bottom end. Okay, using a steel plate here. Okay, so when we compress the cylinder, the steel plate will restrain the expansion of the cylinder in the horizontal direction. Remember, we have Poisson's ratio. When we compress the cylinder vertically, horizontally, it will try to expand about 20% because the Poisson's ratio is 0.2. Okay. So the friction provided by the top and bottom steel plate is very important because if the friction is high, it will try to constrain the concrete from further expanding, prevent the concrete to crack. Actually, the concrete crack because the tensile stress due to expansion in horizontal direction is not caused by a compression. Okay, so as a result, when we change the friction from the top and bottom plate, such as, if we use Teflon sheets, it will reduce the friction. So the constraint effect will be smaller. Okay. Same thing, we use steel brush. Steel brush only provide vertical load, but horizontally, it provides little restraint. So as a result, if we use Teflon sheet, the concrete will crack earlier compared with if we use steel plates. Okay. Even the shape of the specimen has an effect on the strength. Okay. Here, if we keep the L2D, which is the length of the specimen to a diameter, okay, keep this ratio constant, we increase the size, the strength will goes down. Okay. The reason for this is because when we increase the size of concrete, we increase the amount of materials. So for each specimen, when we increase the size, the chance that concrete specimen has a certain flaw, such as honeycombing, will increase. Okay. As a result, when we increase the size of specimen, it will fail early compared to same concrete but with smaller size. Okay, same thing here. If we increase the size of the specimen but keep the same length to diameter ratio, okay, the strength will go down. if we increase the length to diameter ratio, the strength will also goes down, as we can see from the curve on the right. Okay, that is because when we increase the length to diameter ratio, okay, remember on the top and bottom, the steel plate provide constraint effect, prevent the concrete from cracking under tension stress in the horizontal direction. And if we increase L to D ratio, the constraint effect is lower, so the concrete will crack earlier. Okay. All right. Okay. So here we talk about effect of flaws on strength. Okay. The flaws such as honeycombing, okay, or a very weak aggregate in a concrete will introduce so-called stress concentration. Okay. So stress concentration causes the concrete to crack there. Okay. If we increase the size of flaw, we have higher stress concentration, so the strength of the specimen will be lower. Smaller flaw size, okay, by using smaller sample, we have higher stress. Okay, so that's the reason why we increase the size of sample, we reduce the stress because we have a higher chance of flaw, and also the size of a flaw is also increased. Okay, so these two reasons. Flaws are not equally dangerous to all types of materials. Okay, for brittle materials such as concrete, it is flaw sensitive. For soft materials such as rubber, it is not as sensitive to size of flaw. All right, so here shows a typical compressive failure for concrete. Okay. This is stress to strain curve. Initially, we have a straight curve, okay, and we based on this to estimate the elastic modulus of concrete. There's many ways to calculate that, such as E value based on chart, okay, which is the slope of 2 point. Point A is the point with strain of this much. Point B is the stress level to 40% of I prime C. Okay, and there's other ways to calculate the E value of concrete, just for your information. After the concrete cracks, the slope will become flatter, smaller slope. Okay, and the final failure will happens here, and this is F prime C, which is the compressive strength of the concrete. Okay. After that, the concrete can still resist some of the load, okay, but not as high as F prime C. Okay. So depending on the friction on the top and bottom plate, typically we have this popcorn-shaped crack. Okay, that is because in the top and bottom portion we have restraint provided by the friction of the steel plate. So the crack will only generated here and also here. But if we use Teflon sheets, there's not much friction provided by the top and bottom plates. So the crack patterns will look somehow like this instead. Okay, so in this lecture, we summarize what are the parameters affect strength of concrete. Many of these parameters we discussed in early lectures, but some of them we discussed today, okay, such as how the testing method affect the strength of concrete. Okay, and that's the end for today's lecture.